Alright, so we're on section 4.4, properties of logarithms. Remember first, an exponential function is of the form f of x equals a to the x. A is some positive number not equal to 1, and x is just any number. Number 2, logarithmic functions are of the form log base a of x, or I'm sorry, g of x equals log base a of x. A is some positive number not equal to 1. X is a positive number. Alright. And then recall also that these are inverses of each other. Right? That's one. And then also remember, if we have y equals log base a of x, then that's the same as saying a to the y equals x. Yeah? Notice that y then is really just an exponent on the base a. Notice where the base is. Yeah. Alright. So, before I go on, this says that we can write a logarithmic statement as an exponential statement, or we can write an exponential statement as a logarithmic statement. Okay? All right. So, let's go on to some properties. Log base a of 1 equals 0. And again, remember, I can rewrite this exponential as, logarithm as exponential. So, to go from logarithm to exponential, notice I can go like this, a to the y equals x. That gives me that. So here, a to the 0 equals 1. Or I can think of log base a of a to the what power, right? Well, 1 is a to the 0, and that's the exponent, 0. Yeah, same thing with this one. Log base a of a, the exponent is 1, so the answer is 1. And really the same thing as this one. Okay, so I wanted to... Let's look at these first. So this one's a little bit obscure. We'll come back to this one. A to the log base a of m. Notice that's a base a, and that's a base a. All right, but this one, when we're multiplying two numbers, log base a of m times n, we can actually separate that into an addition statement. And if it's a quotient, log base a of m over n, we can separate that into a subtraction statement. And finally, log base a of m to the r is the same thing as r log base a of m. That means we can move r over to the front, assuming that these are going to be defined quantities. Okay, let's look at some, before we look at some examples. So I wanted to prove some of these. Yeah, and so let's look at this one, log base a of m times n. Okay, so how would we approach a proof? So we would say, well, let y equals log base a of m. Let's get a scratch paper here. So we would say this is a proof of number 5. So we would say let y equals log base a of m and x equals log base a of n. Notice that's those two. Okay, so we would then say if y equals log base a of m, that means a to the y, all right? A to the y equals m, and a to the x equals n. Right? We just rewrote that as an exponential. Okay, so if we take rule number 5, so log base a of m times n would be the same as log base a of m is a to the y times a to n is a to the x. Yeah, and that would equal log base a of a to the x plus y, and of course it could be y plus x, doesn't matter, equals, and log base a to, of a to the x plus y is just the exponent x plus y. Right? We get that from this particular one right here. Okay. All right. And x plus y would just be log base a of n plus, and y is log base a of n. Okay. Notice that's what number 5 says, right? That log base a of mn is log base a of m plus log base a of n. Okay, let's look at number 4. So number 4, I'm gonna think of it this way. So f of x is log base a of x, and then f inverse of x equals a to the x. Yeah, they're inverses of each other. So I'm going to apply the composition of each, but in the two different orders. So I'm going to do f of f inverse of x and f inverse of f of x. Okay? So if I apply f of f inverse of x, this would be f of, and the f inverse of x is a to the x. Right? And f of a to the x would be log base a of a to the x. Okay, I'm gonna leave that there. We'll come back to it. F inverse of f of x would be f inverse of, and f of x is log base a of x. And if I apply f inverse is a to the whatever the input is, so this would be a to the log base a of x. Now, what do we know about inverses? Well, f of f inverse of x is just x. And then the second one, f inverse of f of x, also has to be just x, right? So if you look at this last part over here, that's actually the properties 4 and 3, right? So this is 3. Sorry, that one's 3, and this one is 4. Okay, of these properties that were given to us on this list. All right, let's get on to how we're going to use these. All right, so write as a single logarithm and simplify. So this is a subtraction, right? Which means we're going to use this. Or you can think of addition also. Does not matter which way you think about it. All right, but notice this: the coefficients are 1 here. Yeah, the coefficients are 1. So I need to make the coefficients 1 here. Well, we're going to use this rule over here. Oh, I'm sorry. Which rule? This rule right here, right? Which says we can move the coefficient up as an exponent, assuming that these quantities are all defined. So this would be log of x to the 7th minus log of z to the 3rd. And by the way, notice they're log base 10 because they don't have a base listed. Minus log of y to the 8th power. Okay. All right. And I'm going to rewrite it this way. This is log of x to the 7th minus, and I'm going to put these two together, log of z to the 3rd plus log of y to the 8th. This will just make it a little bit more efficient for me. All right, this is log of x to the 7th minus, and I'm going to put this sum together, right? So this says when we add, I'm going backwards this way, I can just multiply the two arguments. Okay, this will be log of z to the 3rd, y to the 8th. Notice I'm just multiplying the two arguments. All right, and then finally do the subtraction. So the subtraction says if I'm doing subtraction, I can write it as a division, right, of the first divided by the second argument. So this will be log of, stays in a log, right, same base, x to the 7th over z to the 3rd, y to the 8th power. Okay. All right, and we'll leave that one for class. All right, let's try number 2. Write each as a sum or difference of logarithms, and again, I'll start with number 1. So this one says 7 log base 3 of, so this is 7 times, and I'm going to leave the 7 out there, log base 3 of, right? So this one, we're going to use this rule. All right, so the cube root of 7z is 7z to the 1/3, oops, log base 3. 7z to the 1/3 power over x to the 3rd y. And that will be 7 times log base 3 of, and the top is going to come out as a sum. Log base 3 of 7 to the 1/3, right, plus log of z, base 3 of z to the 1/3 power. Okay, notice that you just apply the 1/3 to each. or you could actually bring it out to no, you couldn't. Sorry about that. So let's leave it like that. All right. So that's the top. In the bottom, I'm going to subtract minus, oops, this is parentheses around the whole thing, minus log base 3 of x to the third plus log base 3 of y. Notice that's the product underneath, right? So it's a product underneath, so it's an addition of log base 3's. Okay, so this is then 7 times, so these two, I can distribute the one that's out here, log base 3 of 7, bring the 1/3 down, 1/3, log base 3 of 7 plus 1/3 log base 3 of z. Notice again, I'm just bringing down the exponent out to the front. That's this row right here, exponent out to the front. Exponent out to the front. Okay. Minus, and I'm going to apply the minus to each one, 3 log base 3 of x minus log base 3 of y. All right, and then apply the times 7. So this will be 7/3 log base 3 of 7 plus 7/3 log base 3 of z minus 3, I'm going to 7 times, so minus 21 log base 3 of x minus 7 log base 3 of y. Okay. That should be everything. All right. I'm going to stop there, and we'll pick up on the next video.